Hello, good morning Year 10. I hope you are well. Mrs. Allbone here. Welcome to your physics lesson for the triple content. This is the first lesson of the week for week 4, and we're going to be looking at the centre of mass. On your screen you will see the key facts that need to be covered in this lesson, and they are the facts that you need to learn. Okay, so as always we will start by looking at our starter questions. So if you could pause the video and answer those questions. Okay, here are the answers to those starter questions. If you could pause the video again and just check your answers and make sure you are happy with those. Okay, so on with today's lesson. Now we're looking at centre of mass. So if you look here, we've got two designs of racing cars, and you can see that the design of those cars has changed very dramatically if you are looking at a car from the 1920s compared with the modern day racing car. But there's one particular thing that really hasn't changed very much. Now, we need to keep the cars as low as possible. Why would you think that is? Well, of course, obviously we need to keep the cars as low as possible, otherwise they would topple over when the car is turning, going round a corner at very high speed. So we say that they have a low centre of mass. And what do we actually mean by that? Well, the centre of mass is a way of thinking that the total weight of the object acts at a single point, and we call that point the centre of mass. So it's the point at which the total mass of the object can be thought to be concentrated, and that's what we mean by the centre of mass. And you can demonstrate that by simply balancing a ruler on the tip of your finger. The point of balance is at the centre of mass, and you would be able to hold the ruler in place. Okay, so you can see that's exactly what I'm doing here. We have a ruler that's 30 centimetres long and 15 centimetres along is around the centre point. So you can see I'm just balancing the ruler at that exact point. So we would say the centre of mass of the ruler is at this location there. Similarly, I've got a little object here. Now the weight of this bird, most of the mass of this is concentrated in the middle, and its wings are quite light but they're quite far apart. But this has been designed to have its centre of mass at the point of the beak. So here is its centre of mass, and you can see that the bird balances quite nicely there. So the centre of mass is a theoretical point, which is the point at which we can say the total mass of the object is actually concentrated. If you look back at the ruler again, if you think of this ruler as pivoting at this point here, knowing the centre of mass is actually quite useful, because if you wanted to look at the moment of that ruler as it pivots from that point, then what you would actually do is take the mass and therefore the weight of that ruler from that centre of mass position, so from that 15 centimetre position. So if you wanted to work out the moment of that ruler as the ruler pulls itself down, then you would measure it as the weight halfway along the ruler. So the centre of mass can be actually a very useful point of reference from where we can work out things like moments. Okay, similarly, if you have an object, here we have a hanging basket, and if it's moved to one side, then you know that object will swing backwards and forwards until it reaches its equilibrium point. So here the object will have reached its equilibrium point, and we say that a suspended object will eventually come to rest with its centre of mass directly below that point of suspension. So here, if we tilt the basket, it will swing backwards and forwards until it comes to rest. And where it comes to rest, the centre of mass, which would be roughly about here, is going to be directly below that point of suspension. And then we say that object is at equilibrium. So why would a suspended object come to rest at its equilibrium position, and why doesn't it exert a moment? Well, you can see here, when the object is suspended at an angle, you're going to have the weight acting straight down, as it always does, and that's creating a tension in this rope here. Now, part of that tension, if you think about resolving that into a horizontal and a vertical component, the vertical component will be part of the weight that's acting straight down, and the horizontal component will be part of the weight that is pulling this object back to that central position. So we can see we're creating a moment here. We have a force, which is part of that weight, and we have that force acting at a perpendicular distance here from the pivot point. So there's the weight here acting here, there's the line of action of the force, and there is a perpendicular distance from the line of action of the force. So we say that we have created a moment, and that's what's going to make the object swing back down here. When it's in this position and it has come to rest, we see the weight of the object is acting straight down, and the line of action of the weight is along this line, and that's directly in line with the pivot point. So there is no perpendicular distance between the force and the line of action of the force, because they are in line. So there is no moment, and that's why the object comes to rest in this position. We say an object is freely suspended if it returns to its equilibrium position. So if there are no other forces acting on it, then the object will come to rest at that equilibrium position. So if you have lots of different objects, where would the centre of mass be? Well, for these objects it's quite straightforward. The centre of mass is going to be in the centre of each of those regular shaped objects. And we say for a symmetrical object, the centre of mass is along the axis of symmetry. And if the object has more than one axis of symmetry, then its centre of mass is where they all meet. So if you look at these objects here, we've got two regular shaped objects. They have a centre of mass right at the midpoint. We've got one axis of symmetry here, one axis of symmetry here, and that's where they meet. You might be able to see that better on these bigger diagrams. With this object, we've got a axis of symmetry, one here, another one here, and another one here. So at that midpoint is where the centre of mass is thought to be. That's quite simple and straightforward for a regular shaped object, but how could you find the centre of mass of an object that does not have a regular shape? How would you work it out then? Well, it's quite straightforward, and this is a practical that we usually do in the lab, and one that you would be expected to understand. Now, it's based on this principle that we have just talked about. So a suspended object will eventually come to rest with its centre of mass directly below the point of suspension. So when you've got a freely suspended object, we know that its centre of mass will be along a line straight over that point of suspension. And that's the principle that we need to use in order to determine the centre of mass of an irregular shaped object. So if you had this piece of card and you were trying to determine its centre of mass, if we freely suspend it from one particular point, so if we put a pin in there and we let the object move until it came to rest, then we would know the centre of mass must be along that point somewhere, that line that goes straight down. If we then move the object and pin it at a different point and let it move back and forth until it comes to rest, then again the centre of mass must be along this line which is going straight down. If you do this a third time and maybe even a fourth time, you should then start to see that the centre of mass is determined by where all those points cross over, and that will be your centre of mass. Now, how would we do that in the lab? Well, I've got a picture here of how this would look as it's set up. So you have a piece of card, and that's freely suspended at this point here so that it can rock backwards and forwards and then come to rest. And then we have an object called a plumb line, and all that is a piece of string with a heavy object on the end of it, so that piece of string hangs straight down. So where you've suspended the object and you've let it come to rest, that line where its centre of mass must be will be in line with that plumb line, and you can use it to draw a straight line along that piece of card. You would then change the position of the card, so you freely suspend it from the next point, let it rock till it comes to rest again, and then use the plumb line to find the straight line, and again where they cross, that will be your centre of mass. Okay, so you can see I've got this set up here, year 10. So this is my object. If I just move that, you can see, because it's freely suspended, it will come to rest on its own. And so the centre of mass must be straight down here. And then you have a plumb line, which is nothing more than a piece of string with a heavy object on the bottom of it. And if you move that up to your piece of paper, then you can draw a line straight down and you can see where the centre of mass is. You would then take your next point, hang the object from this position, let it rotate again until it moves and until it stops moving freely, and then use your plumb line to draw the centre of mass. And eventually you will have lines crossing at the same point, and that point will be your centre of mass. So you can see on your screen now is a method for working out the centre of mass of a piece of card. So I would strongly suggest you copy that down or write out your own method. And you can see at the bottom here it says you can evaluate how accurate your experiment is, because if you can balance the card on your finger from that point that you have measured as the centre of mass, if it balances at that point, then you know that you have found the centre of mass quite accurately. Okay, so question here, which bus is more stable? One where all the passengers are sitting downstairs, or one where all the passengers are sitting upstairs? Which one would you say is more stable and why? Well, obviously the one that's going to be more stable is going to be this one, but why would that be? Well, it's all to do with the centre of mass. If all the people are sitting downstairs, then the centre of mass is going to be much lower down. So let's say that for argument's sake the centre of mass is at this point here. Now you can see the weight always acts straight down, so if the centre of mass is here, we can say that the weight is acting from here, and that always acts straight down. With the other bus, the centre of mass is going to be much higher up because the people are all upstairs, so the centre of mass is going to be acting straight down from this point. Now, for an object that's leaning over, if the centre of mass still falls within the base of the object, then that object won't topple over. But here, the centre of mass is acting outside the base of the object. So in this instance, that bus would topple over. The last thing that we're going to look at today is this fact that you need to learn about balanced objects, where the sum of the clockwise moments will equal the sum of the anti-clockwise moments. So let's explore that in a little bit more detail. So here we have a seesaw, and you can see here we've got two objects of the same weight and equal distance from the pivot point, which is here. So what do we mean by this? The sum of the clockwise moments must equal the sum of the anti-clockwise moments. Well, if we look at the anti-clockwise moments first, what do we mean by that? Now, the weight of this object, if we look at this side, the weight is acting straight down, but we are moving that object about a pivot point, and therefore we're creating a moment. So although this looks like that's going straight down, we would extend that to go in an anti-clockwise direction. So that's why we're saying that is an anti-clockwise moment. And you can see here that that moment will be 2 newtons times a distance of 0.4 meters from the pivot point, giving an anti-clockwise moment of 0.8 newton meters. If we look at the clockwise moment, that's going to be the same but in reverse. The weight is pushing down in this way. Here's our pivot point here, so we would describe that as being a clockwise moment, and that's going to be the same, 2 newtons times 0.4 meters. That will be a moment of 0.8 newton meters. So you can see here the sum of the clockwise moments is equaling the sum of the anti-clockwise moments, and that means we have a balanced object rotating by a pivot. So that object, those objects are balanced, and that point won't move. What happens if we had a weight of 4 newtons? Where would we need to balance that? Well, again, the clockwise moments stay the same, 2 newtons times 0.4 of a metre, which is 0.8 newton metres. For the object to balance, we have to create a moment on this side of 0.8 newton metres. And we would do that by putting the object at 0.2 metres from the pivot point. So again, we have 4 newtons times 0.2 meters gives a moment of 0.8 newton meters. What would happen if we have an object of weight 5 newtons, and this time we have got a weight of 4 newtons on this side of the seesaw? Well, work out the clockwise moments, which would be 4 newtons times 0.3 meters, giving a moment of 1.2 newton meters. So we need to divide 1.2 newton meters by a weight of 5 newtons to work out our distance, and you will find that that gives a distance of 0.24 meters. 5 newtons times 0.24 meters gives a moment of 1.2 newton meters, and the object will balance. Now, something else that we can do in the laboratory year 10, hopefully we'll be able to do this when we get back, is looking at a ruler suspended at a pivot point here. So the ruler is free to move about this point, and we've got some weights hanging on that ruler, creating a downward moment. And at the same time, we've got a piece of string here which is being held in place, and that is creating a clockwise moment, keeping that ruler balanced in place. And we've also got a newton meter here as part of the setup, so that we can actually measure the force that's being applied to that string to hold the ruler in place. So what would happen if we increase the weight of the load? Now, load is another name for the weight of the object that's creating the moment. So if we increased this weight, if we put more weights on there, what would happen to the force here to hold that ruler in place? Well, of course, the force reading on the Newton meter is going to have to increase. If you're putting more weights on here, you're going to create a bigger downward moment, and so to hold it in place, you need to create a bigger upward moment, which means creating a bigger force. Equally, what would happen if we kept the load the same, but we moved it a further distance from the pivot point? Well, again, the force reading on the Newton meter would also increase because we are creating a bigger moment. Now, I did this at my last school, year 10, so here is the setup that I had, where I had a ruler at a pivot point. We had a 2 Newton weight, 0.8 meters from the pivot point, and we also have to take the weight of the ruler into account as well. Now, the weight of the ruler was 2 newtons, and we used the center of mass to locate its position, which is going to be halfway along that ruler. The Newton meter here, which is being held up, is creating a clockwise moment, and that is being held at 0.4 meters from the pivot point, and the Newton meter reading is 6.5 newtons. So I would like you to have a go at drawing a free body diagram to show the forces on that ruler, and I also want you to show that the sum of the anti-clockwise moments and are equal to the sum of the clockwise moments. So pause the video and have a go at doing that. Okay, so hopefully you have something like this. Here's your pivot point, here's your ruler. The weight of the object of 2 newtons is 8 meters from the pivot point, and the weight of the ruler, because we have to take the ruler itself into account, we talk about the center of mass, and therefore the center of its weight being 0.5 meters from that pivot point, and that's a value of 2 newtons. The tension in the string was 6.5 newtons, and that was a distance of 0.4 meters from the pivot point. So let's look at first of all at the clockwise moments of the tension in the string. So the moment here is 6.5 newtons times a distance of 0.4 meters, and that gives a moment of 2.6 Newton meters. Balancing that are the anti-clockwise moments of the object and the ruler itself. So the anti-clockwise moment of the object is going to be 2 newtons times 0.8 meters, which will be 1.6 Newton meters, and the ruler itself has a weight of 2 newtons times 0.5 meters, which gives a moment of 1.0 Newton meters. When we add them together, we get a value of 2.6 Newton meters. So this does in fact hold out, and we've demonstrated it quite nicely there by that experiment. Finally, year 10, I would like you to have a go at this past question. It's in 2 parts. The first part A is here, and the second part B is here, so please pause the video and have a go at that past question. The Mart scheme is here, year 10, so I would like you to go through that on your own because I'm running short of time on this video. Okay, so that's the end of today's lesson. We've covered everything to do with the centre of mass, what we mean by being freely suspended, and how to find the mass of an irregular shaped object. And we've also shown that for a balanced object, the clockwise moments equal the sum of the anti-clockwise moments. That's the end of the lesson, year 10. As always, please email me if you're having any difficulties with it, and I hope to see you soon.